Okay. You guys had this reading yesterday that you did on the specific heat. Should have been a pretty easy reading. And basically, if the number is high, it heats up slow. The number is low, it heats up fast. So depending on what you need to do, you'll want some things that have high specific heat and sometimes things that have low specific heat. So talked about like how engines, you want to make sure that you have the right materials. So if they have too low of a specific heat, the temperatures will increase too quickly. How water has a very high specific heat, so it doesn't heat up quite so fast. That's good for organisms that need to live in there. Also, how water is used to cool different reactors or engine parts. And then other times, like you want the metal in a pan to have a low specific heat, so it does heat up your food quickly. But then you'll notice like not a lot of your pots or pans at home probably have wooden handles, but a lot of them have plastic. So wood and plastic have high specific heats, and so that means that they don't transfer heat quite as fast, so you're able to get hold on to them. Old school pots and pans might have been made of something called cast iron, so the whole thing is like one piece of iron. And you used to have to use pot holders or something to grab onto the handle because the handle would be just as hot as the pan itself. So parents might still have one of those old plates there. So as far as the questions go here, we have what is specific heat? For that one here, you should have had something probably, I'll go ahead and highlight what you should have here. How much energy or joules can be absorbed per gram to change the temperature 1 degree Celsius? So that should be what you would have had in that. If you do not have the answer correct for these, then you will probably want to go into your Notability, change them, and then resubmit it to Schoology. So when I correct it, I don't correct the wrong one. So you can get your answer changed around here. So take your iPad out, go to Notability, and change these if you need to. So again, that's what I had in terms of specific heat. For a definition. Number 2, what does it mean if an object has a low specific heat? If an object has a low specific heat, it means that it heats up fast, okay, or heats up quickly, or changes temperature quickly, any of those. What materials have low specific heat? So a lot of metals do, lead, copper, iron. You could have listed down really any of these. If you want to list down oil and aluminum, that's probably fine too. Even concrete kind of falls into that category. So really any of these 6, 7 that are on here would be objects that have lower specific heat. Now, aluminum and concrete, they kind of are up there in terms of being a little bit higher. So I don't know necessarily that I would include those, but the first 5 for sure. But if you included aluminum and concrete, it wouldn't be terrible, but they're probably more so in the middle in terms of specific heat. What material, number 4, what does it mean if an object has a high specific heat? High specific heat means that it heats up slowly. So some other things besides water. Water is one that we discussed there, so you want to make sure that you have water down. Wood is another one. So water, wood, plastic, you should probably write down any of those. So for number 4, it doesn't ask us for materials. Never mind. Okay, but again, if it asked you for examples of materials, then you could write that in. Number 5, why is it important for life that water has a high specific heat? So 5 and 6 kind of can go hand in hand, because 5 asks why is it important for life that water has a high specific heat, and what would happen to life on Earth if it had a lower specific heat. So higher specific heat is essential because water is essential for all life on Earth. Since water heats up slowly and loses heat slowly, the water doesn't change temperature as much. And this ensures that animals that live in the oceans or water don't, boil alive, or the temperature of the water doesn't get up as high. And then for man-made structures, it does help us cool engines and reactors. Engines here need to constantly expand and contract due to fluctuations within the heat. That's why we also want to use water around them as well. All right. So again, any of those is fine in terms of water and life, and like I said, you might have similar answers actually for those ones there. And number 7 says, give an additional example of how specific heat is important in our lives in your own words. Again, you just can give another example of how, you utilize materials that have a either a high or a low specific heat. So you can think of, what are times when you want something that has a low specific heat? What are times when you want something that has a high specific heat? So think about times when you need things to, such like copper is used in wiring that helps to conduct electricity. Copper has a low specific heat. That means it transfers through really quickly. There's an example right there. Okay. Otherwise, think of any other ones that you might have had yourself and make sure you have those written in. So if you needed to change anything or whatever, go ahead and resubmit that. So if the teacher needs to, they can pause here so students are able to resubmit. Otherwise, I'm going to move on to our notes for today. Those are going to be found starting on page, I believe it's 25 of your packet. It's concept 4, work and power notes. So page 25 of your packet. All right, and again, if the teacher needs to pause so you guys can get this out, we are on page 25, concept 4. All right, so our last concept here that we want to work on is has to do with work and power, in terms of energy. Now, when I say those two words, you might have different ideas in your head about what those words mean. So we'll kind of go through them. In a physical science sense, they are a little bit different than what you might think. So work. Have you done any work today? All right. If you're thinking about, school or walking or holding some, books or anything like this person is doing here, the answer would be yes. All right. Work is going to be used, we're going to use a capital W. All right. So capital W for work is the transfer of energy that occurs when a force makes an object move. So I have a transfer of energy, so I know that it must involve joules of some sort, and that'll be the units that we measure in. And I know it involves force. So that must involve, force, newtons. So the transfer of energy that occurs when a force makes an object move. All right, so in that terms, you guys probably have done work today, I would assume. So we measure work in terms of joules. All right, so it is a transfer of energy. It is a form of energy, so it will be measured in joules. And two conditions must be met in order for work to occur. All right, so we have to have both of these conditions met. One is the object must move or be moving. All right, so this picture of this person holding this stack of books, you can see that the picture does look like they're in motion, right? They're kind of like in the middle of a walk or a step. So that's helpful in determining that they are moving. But, if the object is just standing there or sitting there or like sitting on a shelf or something like that, then no work is being done. And the force must be applied in the direction of the movement. All right. So the force, there must be a force applied to get this object to move. In the case of moving forward, sitting down, jumping up. Okay. So the force must be applied in the direction of the movement. And again, the sub can pause this at any time to, if you guys need more time to write things down. All right, so you can see it. We have a triangle here. We do have an equation that we use for work. You can just hold off on writing the triangle yet. Let's go ahead and write the equation first. So work equals force times distance. All right, force is my F, D is my distance. Let's go ahead and write down what each of these stand for. So if you need to do this off in the margin area, that's fine. Just as long as it's, you're not running into the practice example or the problem there. So W is work. Okay, that one's pretty easy. It's going to be just the letter there. And that's going to be measured in joules. Force is the capital F there. If you use a lowercase f, we don't really have anything else that we use with F, so that's not the end of the world. I won't, get on you if you use a lowercase f, but you'll see me use capital. And force is going to be measured in newtons. Now, newtons had their own units, right? Newton was kind of broken down into different units. It was kilograms times meters per second squared. You don't have to worry about that. You'll just use newtons, but just kind of keep that in mind. And then D is distance. And so distance it's not so much height, although it could be if you're like lifting something. But it is more so like how far is that force being moved. So it is going to be measured in terms of meters. All right, so D for distance and measured in meters. So now before we do the practice problem, go ahead and write down the triangle if you have not already. If you want to put it in the top corner of your paper or in the margin somewhere nice and big where you can, reference that or see that. And so again, how we use it is that if you look at, the W's on top, the F and the D are on the bottom. That means that they would be multiplied together when you write that equation. If you're asked to solve for F or D, you just sort of cover one of those up, and then you read it as work divided by either force or work divided by distance. So let's take a look at the practice problem, the example. Oh, sorry, I forgot one more thing here. So I added this in here because we are going to be using this equation as well. So if you want to rewrite this one somewhere again on the top of your paper, F, which is force, equals M times A. F equals M times A. So M is, as we know, mass. That's not a whole lot different. A is acceleration, and the acceleration is the acceleration in this case due to gravity. So because there might be sometimes that I give you weight, the weight of an object or the mass of an object, and you're going to have to turn it into force. All right. So a lot of times force can be the weight of an object. But again, if I give you the mass of the object, not the weight, you have to convert it using the equation there. So again, 9.8 per meters per second squared is usually what we use for acceleration, unless the problem tells you that you're pushing it with a different acceleration. But in terms of weight, if we're converting it to weight, then we're going to be using that one. All right. So let's take a look at the practice or example problem number 1. It says you move a 75 kilogram refrigerator 35 meters. So 75 kg, that is a mass, not, anything. That's a mass. This requires a force of 90 newtons. How much work in joules was done while moving the refrigerator? So we always want to start with like writing down what we know, what's our unknown, what are we trying to find out. So it's asking me for work, so I know it's going to involve this equation here, so I'm going to worry about these letters. So W equals question mark because I don't know my work yet. My force is 90 newtons. Now, the 75 kilograms, remember that's a mass, but I might not even need that in this problem. And my distance is 35 meters. Now, I am going to write down that my mass is 75 kilograms, but really all I need is this equation right here. W equals F times D. So although the 75 kilograms was given to me in the problem, I honestly don't even need it because it told me what the force was already. So I'm just going to go ahead and plug in F times D. All right. Give me a second to write that down. So my equation that I'm using to solve is just F times D. And that is 90, which is my force, times 35, which is my distance. And if you calculate that, you'll get 3,150 joules. All right. So again, that one was maybe a little tricky because of the 75 being in there, but as long as you have a force, and it's not asking you to solve for anything else in there, and you have a distance, then you just need to plug in those numbers. Okay, so I'm going to move on. You can pause if you need to. So now under practice time, I want you to, so we should be near the bottom of page 25. I want you to separate this into 4 spots. So either, 4 boxes, they can go like, kind of make like almost like a line down the middle and then a line going across, or you can make 4 lines, kind of going across. Just separate your practice time into 4 spots and then go ahead and number them 1 through 4. So again, on the bottom of page 25, where you're writing these notes, you'll want to separate the practice time space into 4 sections. So sometimes these problems are super easy. They're just kind of like plug in and go, like plug in your 2 numbers and you got it. Other times we might have to do like an additional problem or rearrange the equation. So number 1 says a book weighing 1 Newton is lifted 2 meters. How much work was done? So I'm asking for work. I have the other information here that I need. So work is my unknown. My force, it tells me, is just 1 Newton. And my distance is 2 meters. So I have everything that I need to use this equation. W equals F times D. That'll be 1, which is my force, times 2, which is my distance, So your answer is 2 joules. All right, the next one, number 2, says a 1 kilogram book is lifted 2 meters. How much work was done? Now this looks and sounds similar to the first problem, but the biggest difference is they're both lifted 2 meters. But the second one here gives me the mass of the book, which is not the same as the force of the book. So I'm going to have to convert that mass into a force, aka weight, in order for me to do the calculation here. So my work is still my unknown. My force is technically unknown too, but I'm going to use the m times a in order to get it. And then my distance is known already at 2 meters. So this problem can be done 2 ways. So I'm going to show you kind of it can be done in 2 parts. So first solving for f and then plugging the f into the equation. The second way that I show you is the optional way that you can do it, where you kind of just plug in m and a for your f and then just solve it all together. So I'll show you. You can write down both ways, or you can write down one of the 2 ways, whatever one you want. It's either way you'll get there. Okay. Sorry. So the mass is 1 kilogram. Now mass normally I wouldn't need, except I have to have that now to solve for force. And your acceleration is 9.8 meters per second squared, because that's just given in terms of when you're talking about lifting something. All right, so here's how it'll look if you want to solve for force separately. So force is mass times acceleration. So I'm just going to literally plug in 1 and 9.8, multiply those two. And the fact that it's 1 gives me 9.8. All right, now again, 9.8 is not my answer. Now I'll have to take my work equation, work equals force, which is 9.8, times distance. Plug that in. So work equals force times distance. And we have 9.8 times 2. All right, so when you do 9.8 times 2, you'll get an answer of 19.6 joules. All right, so that one showed like 2 separate equations to solve in order to get there, and that's totally fine. Another one I'll show you here, or another way to do it, is just sort of, like I said, kind of work it into one equation. And so I know that work is equal to F times D. If I need to break force apart into M times A, what I could do is put it all together. So work equals force times distance. So this is option 2. I'm still going to get the same answer, but this is maybe just a hair less work. So work equals force times distance. Again, what I'm substituting here is I'm putting the M times the A in for the F. So it looks like MAD, M times A times D. And then I simply plug in all 3 numbers. So my mass, which is 1, my acceleration, which is 9.8, and then my distance, which is 2. So again, you can see I just, instead of doing 2 separate problems, I kind of combine them into one. And that also equals 19.6 joules. So either way will get you there. It's up to you, depending on which one you want to use. All right. Okay, let's take a look at 3 and 4. So 3 says 250 joules of work are needed to push a box up a ramp. The force needed to push the box up the ramp is 10 newtons. How far up the ramp was the box pushed? So this one is different. It tells me I have 250 joules of work and I have a force, 10 newtons. How far up the ramp was the box pushed? So my work is 250 joules. My force is 10 newtons. And my distance is unknown. All right, so for this one, it's best to use the triangle. All right, so you have your the triangle up there. You cover up distance, and then you can visualize that as W over F. So W over F, W divided by F. So go ahead and write that out. And then you just simply plug in those numbers, 250 divided by 10. And after a quick calculation, you should get 25 meters. Again, answer is distance in meters. All right. So again, that one required us to rearrange the equation to solve for distance. This next one here will be similar, but we're going to rearrange the equation to solve for force. So 4 says if 56 joules of work energy is required to lift a dumbbell to a height of 7 meters, what is the weight of the dumbbell? All right, so we're looking for, it asks me for weight, right? And so it's important for us to remember terms. Remember, weight is the same thing as force. It's not asking me for the mass of the dumbbell. It is asking me for the weight of the dumbbell. So it's asking me for force. So I'm just simply solving for force here. So my work is 56 joules. My force is unknown, aka weight. And my distance is 7 meters. So now when I look at the triangle, I'm just going to rearrange the equation by covering up the F. I can visualize the W over the D. So force equals work over distance. Work over or divided by distance. So that becomes 56 joules divided by 7. And some of you might be able to do this without a calculator. It'll give you a nice even number of 8. So again, that's a lowercase w there in terms of the answer. So not the work, but your weight equals your force, which equals 8 newtons. Okay. All right. So let's move on to the next page, 26. We're going to learn about power because this concept was titled Work and Power. So power is going to be defined as we're going to use a capital P for this. Before we use a lowercase p for momentum, I believe, but for Power, we use a capital P. We haven't discussed momentum in a while, and you won't see that on the test, so don't worry about getting that confused. But uppercase P for power. So this is the amount of work done in a certain time, otherwise known as the rate at which work is done. So it involves work and it involves time. I can tell that from this description. So it involves work and it involves time. So the equation that we're going to use for power, and we'll also write a triangle for power too. The equation that we use for power is actually a little bit, I'll show you guys once we're done writing the original equation, but we can also sort of, kind of sub in letters for that equation too. So here's the equation for power. Go ahead and write this nice and big under that space there. Work divided by time. Power equals work divided by time. So let's go ahead and we'll identify. Well, I guess, okay, sorry with that. I was going to identify all the letters first here, but I'm going to go over the other possible equations. So what I will do sometimes is I will give you, instead of giving you the work in terms of like if I ask you to solve for power, I might give you the force and the distance and the time and ask you to solve for power. Now, basically what that you're doing is you're substituting F and D in for work, which we just learned about, right? So we just learned about F and D, that stands for work. You can sub that in here and it'll look like this, okay? So these two equations are the same thing. You're just substituting work in for force and distance. So go ahead and write that one down as well. And at the same time, I can break down force into mass times acceleration, and then I can use that times your distance to get to work, and then I could possibly divide by time. So this is the third one here. Again, all these equations, believe it or not, still solve for the power. It's just a matter of what you need in terms of the equation that's given to you, and how many other side equations do you need to do to solve for these? So, the first one is our main equation, but, some people like to see the other possible ones, written out too. Again, all of those in the numerator spot, the top spot, all equal work. Work is force times distance, and work is also mass times acceleration times distance. But all of them are over time. Okay, so that's where we get the rate from. All right, so P is for power. Now, power units are going to be a little bit different, okay? Power units, we are going to use, we have two options, and I don't care which one you use. Since work is joules and T is seconds, we have joules per second. That is one of the options that you can use. We also have another, like a term that can be substituted in for joules per second, and that is watts, W-A-T-T-S. And the only thing that gets a little tricky with that is that it does use a capital W for the abbreviation. Now, some students might get a little confused because you have W for watts and W for work, but you are welcome to use joules per second or W for watts. Or if you want to write the word watts out instead, that's also fine too. Okay, W is work, as we know, and that's measured in joules. And T is time, which you would have guessed, and we're measuring that in seconds. So this time, it's a lowercase t, not a capital T like we've seen with temperature. So we're going to be measuring it in we're looking at a lowercase t for time. So again, you might have to squeeze some of this in your margin areas too. Here is the triangle that we'll use for power. So power equals work divided by time. So that's why we put power in the lower left corner, work on top, and time in the lower right. But again, if I need to solve for time, I can rearrange the equation and take W over P, work divided by power. Or if I need to solve for work and I'm given power and time, that'll be work equals P times T. All right. So the last thing that we'll do is this practice example problem here. Example problem number 2. So it says it took 150 seconds to move a refrigerator. You did 3,150 joules of work in the process. How much power was required to move the refrigerator? So this is similar to that one problem that we did. We did come up with 3,150 joules of work. So now we're taking that amount of work and we're going to end up dividing up using the time to find the power. So what was the power in terms of watts or joules per second that was required? So power is my unknown. I do have my work, 3,150. And I do have my time, 150 seconds. So this one is just kind of a straight plug it in and go. So power equals work divided by time. That's the equation that I'll need to use to solve for P. So I plug in 3,150 for work and 150 for time. Again, watch your units. If I were to give you something in minutes, you would have to convert that to seconds first. And then for an answer, you'll get this, 21. So again, here's your two options as far as putting your, well, there could be 3, I guess, 21 joules per second or 21 watts, or you can write 21 W. Okay. So that is all that I'm going to have you guys do for today. And this was a lot to get through, so just wanted to make sure that we got through all of that together here. If you have any questions, please let me know. Bye. Thanks.